So one announcement at the beginning that not going to be here at the very end of the presentation, but I asked my colleague Tamás, and he's gonna get my role at the end, and he will manage the questions. The format is everyone will gonna have 10 minutes to present, and then hopefully 3 minutes questions after each block. And so please, we try to keep this 3 minutes. If you have too many questions for some reason, I think at the very end you can come back and ask your questions which remained important until the end. So first I'm gonna introduce Mir, one of my students, and I'm gonna give for each person a short bio, and then I'm gonna give my personal point of view as well, so everyone knows about the background of Mir and also our collaboration. So Mir is a passionate robotics researcher. He graduated with summa cum laude in electrical and electronics engineering from the American International University, Bangladesh, and is currently pursuing a master's degree in the Erasmus Mundus Joint Master Program in Intelligent Field Robotic Systems, or IFROS, funded by the prestigious Erasmus Mundus Scholarship. His research focuses on deep learning, computer vision, motion planning, and robotic manipulation, with the goal of advancing the capabilities of intelligent and autonomous robotic systems. What I was thinking what to say about Mir, and the things which came to my mind firstly was autonomy. I remember really well when sometimes we created some data set and we put it on a shared Google Drive link, and we had the meeting in like 2 days or 3, so I didn't specifically write an email about it because I didn't feel that it's that urgent. But by the time of the meeting, Mir already saw the data set, and he already downloaded it, he already trained it, and he even get results on the meeting where I wanted to introduce him the new data set. So this was really amazing. I really like this kind of mentality. And obviously what really tells a lot is that he already prepared an article, and we are finalizing it in this week, probably going to submit it in next week because or soon. So I would like to give the floor to Mir. So please share your screen or your slide, and you can start your presentation.
Thank you for your bio. I will now share my slide and start presenting.
Perfect.
Hi everyone. Myself Mir Mohibullah Sazid. Today I'm going to present my master thesis about sim-to-real transfer learning for object tracking in robotics application. In this presentation, we addressing everything as we for styling purpose, although all the results are here is done by me. So at first I will discuss about the introduction, then contribution, and at the end I will give a outcome of the thesis as a conclusion. So let's start with the introduction. So what is object tracking? Object tracking is something where we track the objects in between the frames and by given an assign ID. Here you can see in the video the football players are being tracked over the frame with a assign ID. And object tracking can be used in different parts of robotics like navigation, manipulation, human-robot collaboration. But the main problem here, we need a large amount of data set to train the object tracking models, but they are costly and to collect the dataset and label them. So we can use synthetic dataset where we can create fast, large-scale annotated dataset using different techniques to bridge the reality gap, like domain adaptation technique or domain randomization technique. Here we will be using domain randomization techniques. So the main contribution of our project here, we will be converting any 3D CAD models that can generate synthetic dataset without any manual annotation. We have introduced ablation study where we show which randomization techniques are most effective in sim to real domain, and we also give dual pipeline benchmark. One is detection-based tracking and another is segmentation-based tracking. And also we have created the publicly available dataset for real world with 23,000 annotation for 2.5K frames. So the main methodology here, we need to create the 3D models of the objects, and where we use different randomization techniques to generate the dataset, which will be automatically annotated as well. And here for the training, we use a pre-trained weight for COCO dataset for stable training. And for in the real domain, we captured the real world dataset and manually, and we do it by manual annotation and then evaluated it with the model trained. So here we used 7 randomization technique. One is object placement, another one is hue offset, and color randomization technique, object rotation techniques, as well as we change the background of the object for randomizing different background, and we also randomize the lighting. And for oscillation for object tracking, we also introduce object overlap. For the dataset we created, here in the video, you can see the dataset video, one of the dataset video, where we include motion blur, oscillation, dynamic lighting, and overlapping object. We also make sure that there is a balanced class distribution, and the annotation follows the MOT style challenge format. For synthetic dataset, we create 7 different dataset. In the dataset 2, you can see we have introduced all the randomization techniques that I told you before. And in the dataset 5, we have introduced only 3 basic randomization techniques, which are more of basics. And for dataset 4, we introduce how the object overlapping is affecting the for sim to real transfer. And for dataset 7, instead of Poisson-Dick sampling, we use uniform sampling, where we showcase how our Poisson-Dick sampling object placement is working better. So these are some of the generated images. Here you can see the two objects overlap. Here you can see like 5 objects are overlapping. Here this is the uniform sampling, and this is without the background textures. And here for the result section, you can see for the detection in dataset 2 and 3, we got the best result in for multi-object tracking accuracy. And in dataset 5, where only 3 basic randomization technique was used, goes almost to my negative point. And but although the results was good in dataset 2 and 3, but dataset 3 has the most better result because the body and bonnet has visual similarity. As a result of that, the overall micromota, where we calculate the mota for each class, goes very low. Here in the right side, you can see the object in zero-shot transfer, where no real images was used. Only using the synthetic dataset, we got around 80% mota score and around 68.5% micromota score. And for one-shot transfer learning, you use one single real-world annotated frame, which was copied 700 times and co-trained with the synthetic dataset, and we can see a boost in every classes, especially in the body and bonnet class, and overall we got around 22.8% boost. Now I will introduce the segmentation-based tracking, where we got the most better result with 5 object overlap, and we got the lowest result in where only the baseline was used. And for the segmentation-based tracking, here you can see as in segmentation, it is pixel-wise shapes is measured. That's why the micrometa is lower because of the visual similarity between the body and bonnet class that I have mentioned earlier. And here you can see using the same training technique, we got better result for one-shot transfer using single real-world annotated frame. And the performance was boosted to 87% micromota and around 90% mota score. So the conclusion is here we created a fully domain randomization technique for sim to real transfer. This used for Poisson-Dick sampling control overlap, which can create thousands of data in minutes. And we showcase that how synthetic dataset can be used in real world, and minimal supervision can improve the real world performance. And we also showcase how the lighting and background texture improve the overall efficiency of the dataset. We also compared the result shows that the bounding boxes tracker is more accurate and 1.5% faster. So thank you for your attention. If you want to go in detail about the thesis, you can scan the QR code here or see my website to see my books where you can find every details. Thank you.
Thank you, Mir. Thank you very much. It was a really interesting presentation. So I would like to ask if anyone has a question regarding this presentation. Okay, Gabor, thank you. You can.
Just a short question. I don't really understand what is the difference between tracking and classification. So you use the tracking as that every picture is classified, and you basically follow in this way the motion of one particular object, or you use some other tactics.
In object tracking, the main thing is like if you are detecting on object, you will be collecting pictures, like taking pictures of the things. Like here you can see in the video that if we take a pictures here, like for example, there is a hand in between them, you cannot know where the object is. The tracking is more useful like in these kinds of scenarios where the object, where you can track the object in between the frames in real time, so that if someone like if something wants to pick the object and place it, then it can easily track the object and place the object. But in detection case, we cannot do it because it won't be detecting that when there is something in between them.
I would just add a real quickly here that basically in the video you can see the IDs, and it's the same class, they have different IDs, and so the IDs move with the specific object. While in object detection we don't have IDs, we just have detections of objects with classes.
Yes.
Okay, I will have like a short question as well. What was the main difficulty in your research, and what do you think the improvement could be for future work?
The main difficulty was in tracking. The main problem is the object is moving, so you need to track the object. Like in some of the cases, the objects are overlapping. So if we just do the uniform distribution or the Poisson-Dick sampling based distribution, when the objects are overlapping, you cannot know the perfect. It can generate re-ID. Like suppose one ID was 1, then if we pick another object when it is overlapping, it can re-identify as a new object. So this is one of the reasons that we have used object overlap. And in the future, for the segmentation based tracking, we can introduce more advanced segmentation based model, or we can use the shapes properly to showcase that how it can be improved in terms of segmentation, because in detection we already got a very good result, which is around 94%. So yeah.
Thank you very much. So I think we should move on to the next presentation, but if you have any question, you can ask at the end, Mir, as well. You can ask your questions at the end as well. So the next presenter is going to be Soma Seres. So Soma is an AI-focused MSc student finishing the EIT Digital Master's School's double degree program in autonomous systems. He spent his second year at the Eötvös-Loránd University after completing the first year at KTH Royal Institute for Technology. His work focuses on 3 degrees of freedom pose estimation, synthetic data generation, and sim-to-real transfer learning, which he explores through his research at Hunra and Stucky. He earned his bachelor in computer engineering with the highest honors from the Budapest University of Technology and Economics in 2023. So the things that came to my mind with Soma is that his responsiveness, his proactiveness and ambition. I always, when I texted about something like on Elements, then he was texting me back immediately, even if it was out of office hours. So it was really, I really liked this kind of mentality. Also his proactiveness that we were working on the same repository of data generation. And when there was some open issues that I didn't have time to deal with, I didn't even ask him to deal with them, but he said, okay, I want to do that. And then he solved some serious problems in the repository. So it was really good to have him on the team. And yeah, and that's and he had also a quality research, and hopefully we're gonna have an article out of this research as well soon. So I give you the floor and you can share your slides.
Thank you for the kind words and welcome everyone. Today I will present my master thesis titled Sim-to-Real Transfer Learning for 6 Degrees of Freedom Pose Estimation in Robotic Manipulation Applications. And my supervisors were Zoltán Istenes from ELTE and Dániel from Stucky. So the outline of the presentation is as follows. First, I will introduce the problem and then present the proposed method, followed by a case study and its evaluation, and finally a short summary. The problem statement, the context of the work is the 6 degrees of freedom pose estimation task. Here we can interpret the pose of an object based on the translation and rotation relative to the camera position. And AI-based models are an intuitive choice for this problem as they performed well in several computer vision tasks. However, these require large amount of detailed and precisely labeled data, which is, of course, costly and time-consuming to collect. So one solution to this is sim-to-real transfer learning, which addresses this by using synthetic data, and label generation can be automated. This is a special case of transfer learning, where we transfer knowledge from one domain to the other, in our case, sharing the same task, which is the 6D pose estimation. However, there is still an issue, which is the reality gap, which means the performance drop when moving from the synthetic to the real domain. This still remains a challenge, and one promising solution to this is domain randomization, which I have investigated in my thesis. So in my thesis, I proposed 3 research questions. First is, how do different domain randomization configurations affect the model performance in this task? The second is about how effective is fine-tuning with custom synthetic data, and how strong is the original model's training bias. And finally, how can we utilize few-shot fine-tuning and how does it affect the performance? And comparing it to training on a mixed real synthetic data set from the beginning. So the method is as follows, which is my main contribution of my thesis. It is a domain randomization method for generating synthetic 6 degrees of freedom pose estimation datasets. The input is the 3D models of the target objects and the configuration parameters, from which the objects and their initial poses are generated, along with the camera positions, and the whole scene is loaded into a physics simulator, which is then run for a few steps, and then the images are rendered and post-processed, and also the automated label generation is implemented in the pipeline. And finally, the output is the dataset, which includes RGB and depth images, as well as 2 types of masks, one for the full objects and one for the visible parts. And of course, the ground truth poses, which means the rotation matrix and the translation vector. And finally, some additional metadata like the bounding boxes of the objects and the pixel counts on the segmentation masks are also calculated. For the case study, I have created a new data set, which is called INO6DOF590, where INO stands for industrial objects and 5 stands for the 5 selected components, which we can see on the slide here, and 90 stands for the total number of images in the data set. Both the RGB and the depth data is provided, and the data set is labeled manually. And there are 3 types of scenes in the data set. First, this one with the grid palette captured from above. Then we have the black background with the objects also captured from above. And then finally, we have an elevated side view over a black table. Training was also implemented and integrated into the pipeline. And any model that supports the widely used BOP dataset format can be integrated easily. During my thesis, I chose one specific model called CozyPose because it has the training code available publicly, and I generalized it to support arbitrary BOP datasets, including the synthetic datasets generated. It is an RGB-based method with 3 modules, first the detector, then 2 estimators, which yield a coarse estimation of the poses and a refined estimation. Okay, for the experiments, I have designed a few experiments for the research question specifically. For the first research question, I tested 3 different domain randomization options. One of them is post-processing noise, the other one is distractor objects, and finally randomizing the camera position, having it fixed from above or elevated and sampled from a sphere around the target objects. And you can see a few examples at the bottom of the slide. For the second research question, I have compared the original generator of the CozyPose model and my proposed generator, and I have also tested a larger dataset size to check the effect of using more data. Finally, for the last research question, I have created few-shot datasets with 3, 6, or 9 images evenly sampled from each group, and these were used for first the 10-epoch fine-tuning for the pose estimation components, and then I also trained the models from scratch using a mixed real synthetic datasets. Okay, for the evaluation, I have used the widely used metric in the field called the symmetry-aware average distance metric. And to ensure fairness, I've also came up with 2 custom metrics. One is combining all the groups into a merged dataset and evaluating with this metric overall, and the other one is taking the average across all groups. So for research question 1, the results can be seen on the slide, and we can see that the best performing model came from the dataset with noise and the spherical camera position and not using distractors. Then proceeding to the second research question, we can see that using more images performs slightly better. More importantly, we can move on to the bias question part. You can see that using the mixed CozyPose and DataGen method performed better than just using the DataGen. And the most important aspect and finding is that using just the CozyPose generator was the best performing one. And this suggests a built-in bias despite having similarly looking images. And finally, for the few-shot fine-tuning question, we can see that 3-shot resulted in a minor improvement, and 6 and 9-shot are similar, and they resulted in a significant improvement. And finally, comparing the different training methods, the 0-shot, the few-shot fine-tuning, and the mixed training, we can see that the mixed training from the beginning with the merged dataset performed best, and it was able to achieve a stochastic dominance over the other methods, as we can see on the performance profile graph on the bottom. Finally, some qualitative analysis as well. We can see a few of the best results here on the slide. We can see that all the poses are correct and the translations as well. And to move on to some erroneous cases, we can see that sometimes the misclassification messes up the estimation. We can see here a misclassified object. Then we can also see that the rotation of the handle and the bonnet parts are not always precise, especially if they are flipped. The models have issues with estimating the orientation. Finally, to summarize, we have some future works related to the thesis. I'm currently running more experiments to improve the synthetic data generation part, and we are aiming for a publication this summer. And other directions include exploring domain adaptation methods as well. And it would be also beneficial to find an RGBD method and try the different depth domain randomization methods. And to conclude, my main contributions are the extended DataGen framework to support this task, having generalized a publicly available model and integrating it into the pipeline, creating a new benchmark dataset, and also, last but not least, conducting experiments to answer the 3 research questions, which can be seen here. And that concludes it. Thank you for your attention, and I'm happy to answer any questions, and you can access the full thesis via the QR code.
Thank you very much, Soma. And so the floor is for the question if anyone has any. Imer?
Yes, thank you for the presentation. I would like to ask what physics engine have you used? Because you mentioned that you you use a physics simulator, but maybe I missed it. But
No, I didn't mention it. Good question. Thank you. We have used PyBullet because it was already integrated in the pipeline, which I extended, and it is also very lightweight and easy to control the scene and get the images and the labels as well outside the simulator.
Okay, thank you.
Thank you.
Tomasz?
Thank you for the presentation. Do you have any ideas how could you improve the handling the symmetry of the objects, like the handle and the bonnet, maybe that is symmetric?
Great question. I think it would be beneficial to design some kind of method that focuses on generating data that captures these objects specifically from different angles and from different positions, and to focus a bit more on ensuring that the data generated covers this space, because orientation and rotation especially is very, like, it's a continuous state space, so it's very hard to capture this. And I think it would be beneficial to focus on this more specifically in the data generation part.
Thank you.
Thanks.
Thank you. For me as well, last question is that, oh no, then Emma has the last question then.
Sorry. Yeah, so it was a great presentation. Thank you so much. And my question is that if you had a couple of extra months, is there anything that you would have done differently in your research, or something that you would have included in your master thesis?
Yes, thank you. Amazing question. I wanted to experiment a bit more with the domain randomization methods, but unfortunately, I had to select 3 types of domain randomization to include in my first research question. But I want to explore a bit more, and this is what I'm doing right now to enhance the base performance of the DataGen framework. So we are at the point where we have full control over the data generation. Now we just need to figure out which is the best setup. So this is what I'm doing exactly.
Thank you. And is this something that you also want to include in your article, or?
Yes, exactly.
Okay.
Yeah, this is the main goal. Yes.
Thank you.
Thanks.
Thank you. Yeah, and I want to just add at the end that it's a really hard. I feel it's a really hard master thesis, 6 degrees of freedom pose estimation. I actually at the beginning I wanted to talk out of it, Soma, to find something easier topic, but he said he wants to be ambitious, and he was ambitious, and at the end I think it was a really high quality master thesis as well. So
Thank you.
So next, I think it's better not to hurry with the introductions of the students. So for this reason, I'm going to introduce both of them after each other now, because now I still have time. So first, you're gonna hear the presentation of Syma, and Syma is currently enrolled in the Erasmus Mundus Joint Masters in Intelligent Field Robotics, Robotic Field Systems, sorry, or IFROS in the short version. where she has developed expertise in advanced robotics, AI, and sensor fusion across multiple European institutions. She received her bachelor degree from the Department of Electrical, Electronic, and Communication Engineering at the Military Institute of Science and Technology in Bangladesh. Her research interests span robotics, reinforcement learning, deep learning, human-robot interaction, and autonomous vehicle. She aims to create innovative solutions that make intelligent systems more adaptive, robust, and human-centric. My personal connection or my personal opinion on Syma, the words that came to my mind is ambition, determination, and precision. So I remember the first interview with Syma, and then she was telling me that she wants to do reinforcement learning. And I was afraid a bit at the beginning because reinforcement learning is really hard topic and it's really easy to underestimate the depths of reinforcement learning. I know it for my own example because I did that in my PhD, during my PhD studies. And but she was very persistent. I couldn't talk out of it, out of it. And she at the end, and it was really good. She really she read the book I gave it to her really fast and reproduced the state of the art also really fast. And I think at the end it's a really good master thesis, and not just a master thesis, but also she prepared an article which we're gonna submit shortly to a Cuban journal, and so it's a really good collaboration that we had. Also, I want to point out that the first two presentation was about the sim tutorial work that I was concentrating during my PhD, and this will concentrate on the reinforcement learning. It's gonna connect to the other line of research that I did with my PhD, and she really took it to another level. And before I give you the floor, Syma, I want to introduce Selin as well. So Selin holds a double major in electrical and electronics engineering and media and visual arts from the Koç University, where she developed a strong foundation in both technical and creative disciplines. She is currently finalizing her master's degree in intelligence field robotic systems as an Erasmus Mundus scholarship holder with a focus on urban object detection for autonomous navigation. Her research interests include field robotics, robotics perception, and the integration of technology and real-world environments. Selin brings a multidisciplinary approach to engineering challenges, shaped by both her academic background and international research experience. I would like to add for Selin that her internship was at the Autonomous Mobility and Perception Lab, or AMPL, at the Universidad Carlos III de Madrid, and I was a supervisor as an ATA supervisor, so not a Stucky supervisor here, but I was thinking it's interesting to show her work as well in this Stucky webinar. So as she was working in Madrid, she working from Spain, we had online talks, and as well, she was more closely collaborated with her laboratory in Madrid, but still, with this time, I could establish a sense of determination, goal orientation, and reliability. She was really persistent. She knew what she wants to do, and she executed it in a good quality. I really liked collaborating with her, and I was more like the academic guide for her research, and the professional guide was more from the laboratory, but I think it was a super good master thesis as well. So first I'm going to give you the floor, Syma, and I asked Thomas to get on with managing the meeting, and I'm going to disconnect, but I'm going to reconnect with my phone, and I'm going to listen the whole time. So Syma, you can start your presentation.
Thank you so much. I'm sharing my screen. Can you see my screen?
Yes, it's good.
Yes.
Okay, thank you. So my name is Syma Afsha. Today I'm presenting my master thesis, Enhancing Deep Reinforcement Learning with Curriculum Learning for Robotic Tasks. My thesis is supervised by Dr. Dániel Horváth and Dr. Zoltán Stenas. So let's get into the topic. So in this presentation, I will be covered these topics. The first, I will be presenting about the problem statement of my master thesis. Then I'll talk about the methodology, and following this, I will at last I will talk about the summary of my master thesis. So now I'm talking about the problem statement. So deep reinforcement learning has been well established in the gaming industry, but it struggles in robotic environments. The challenges in sparse reward continuous state action spaces due to three main problems. That is, the first one is the inefficient exploration. The robot could not explore the data really well. The second one is the low sample efficiency. And the third one is the training instability. So now I'll be talking about my contribution of the master thesis. So I have implemented three novel curriculum learning strategies for boosting the performance of deep reinforcement learning agents. The first one is the incremental graded curriculum, IGC. That is the gradually expands task complexity based on agent performance. Then the second one is the dual buffer mechanism that separates the positive and negative experience for balanced replay. The third one is the dual mechanism incremental curriculum learning, DICL, that is the integration of incremental graded curriculum and the dual buffer mechanism in a unified pipeline. That is the optional strategy of the hindsight experience replay and the prioritized experience replay for advanced replay. Here you can see the schematic of the dual mechanism incremental curriculum learning framework. As I have mentioned in the previous slide, that my contribution is the three curriculum learning strategies: the incremental graded curriculum, the dual buffer mechanism, and the dual mechanism incremental curriculum learning. So here you can see the green one is the incremental graded curriculum that expands the task difficulty based on the agent performance. The blue one is the dual buffer mechanism, and the integration part of incremental graded curriculum and the dual buffer mechanism is the dual mechanism incremental curriculum learning framework. So here the main thing I did is the negative experience, like if in the environment, if any penalty event occurred, then the negative experience goes to the negative buffer. And if there is no negative reward, negative penalty event occurred, then the all experience will goes to the standard experience replay, with the optional integration of the hindsight experience replay and the prioritized experience replay. And if the condition of the condition meets, then it goes to the positive buffer. Then all the experiences is sampled based on the sampling, like you can see here is the zeta post and zeta neck. Then it combined all the batches. Then the gradient update on SAC agent, as I have used the SAC as our agent. Then it update the policy and critics, and the action executes by the environment. Then environment gives the state and reward to the agent. So it will be in loop. And here in the evaluation part, there are three challenging tasks I have evaluated, like the fetch in the gymnasium fetch benchmark. The first task is the fetch pick and place. The second task is the fetch push, and the third one is the fetch slide. So as I have mentioned, there is a penalty event occurred in the environment. So in this case, you can see from this video that if there is the object fall off the table, then then the penalty is -100, and if there is no penalty, then there's 0. So the three main configurations for this evaluation is the baseline compared with our first method, the incremental graded curriculum. Then the second one, the baseline with the drop penalty with the dual buffer mechanism, and the baseline with the drop penalty with the dual incremental curriculum learning. So here we also compared with the strong baseline here, the state of the art curriculum learning strategy. And here you can see in the figure that if the figure of the confidence intervals here, if there is a wider confidence interval, then there is a like a greater variability in seeds. So we use 3 random seeds for the training. And if it's narrow, then there is not greater variability in the seeds. And here you can see in the table our aggregate results across all tasks, that our incremental graded curriculum with hair and pair in the pick and place task got like 100% success rate and 0% optimal gap. And with the incremental graded curriculum with the hair got 100% success rate, and also with the 0% optimal gap. And also our second method, dual buffer mechanism, also with hair, also got 100% success rate in the pick and place task. And also our DICL also got 100% success rate in the pick and place task. And for the pushing task, our incremental graded curriculum with hair pair got 100% success rate with 0% optimal gap. And dual buffer mechanism plus hair also got the 100% success rate. And for the sliding task, incremental graded curriculum with hair and pair got 98% mean and 0.02% optimal gap. So now you can see that that I have compared with the baselines with our methods. Like for the pick and place task, dual buffer mechanism with hair exhibits the most rapid convergence. For the pushing task, dual buffer mechanism with hair exhibits the most rapid convergence for the pushing task compared to the baselines. And also the sliding task, IGC plus hair plus place demonstrate superior over all performance. So the main comparison between here, the state-of-the-art curriculum learning strategy, and our method, that here stores only successful episodes, and our method stores successful and unsuccessful failure episode. So it explicitly learns from both success and failures. That is the main difference between these. So here you can see the qualitative evaluation of our methods. So for the fetch and pick and place task. So you can see that maximum success rate 100%, minimum success rate, it mean success 100%. That's a pushing task. You can see the maximum success rate 100% and mean success rate is also 100%. And here is the fifth slide. You can see the maximum success 99% and mean success rate 98%. So now I'm talking about the summary of my master thesis. So we introduced a novel curriculum learning strategies to address persistent challenges in deep reinforcement learning for sparse reward and continuous control tasks. And our incremental graded curriculum, IGC, adapts task complexity based on performance, accelerated early learning. And our dual buffer mechanism uses separate positive and negative replay buffers, improving stability and sample efficiency. And the integration of incremental graded curriculum and dual buffer mechanism, DICL, dual mechanism incremental curriculum learning. These methods outperform baselines on robotic benchmark. So the result is faster convergence, improved stability, and higher success rates. So our future work is to apply the real world robotics to measure sim to real gap and extend to multi-agent and hierarchical scenarios for improved stability. Thank you for your attention. If you have any question, you can ask me.
Thank you, Simon, for the great talk. I will open the questions to anyone in the audience. Please go ahead.
So Dániel mentioned that you were quite motivated to do reinforcement learning, although it's a harder topic. So my question is, did you run into any unexpected challenges during your research?
Yeah, yes. Like I have like implemented a lot of things because it's like it varies. Like first time the success rate is low, then I have to implement it at other things. Like I have implemented like adaptive, fully adaptive, self-paced adaptive, and the predefined one. So I have to like implement it if this fixed one works better, or the predefined one works better, or adaptive one works better. So I have like implemented like many equations to like solve this. Then I got this at last. So this is the most challenges thing I have faced in this thesis.
Thank you.
I also have a question if there's no other. I see that reinforcement learning is a tough topic in itself, but my question is about experiments in real world with real robots. I see that you have no time for that, or didn't have time for that. What do you think would be the biggest challenge if you wanted to deploy in real life with real robots?
So the biggest challenge I can face about the environment. Like I have to like if I want to pick and place, then the object positions and with the simulation and the real world should be like similar, so that it can successfully pick and place, or pushing task or sliding task, whatever. So the environment can be challenging, but our result like shows really well results. So it can like I think it will be great in the real world environment.
Thank you. Is there any other questions? If not, then thank you again. And I would like to ask Selin to share her screen and her presentation.
Are you able to see well?
Yes, and now we see the full screen shared.
Yes, amazing.
Right. Thank you.
Thank you. Good afternoon. I'm Selin, and I will be presenting my thesis project titled Urban Object Detection Using Sensor Fusion for Autonomous Navigation. This work focuses on improving the detection of small but critical urban objects, which are poles, by integrating 2D deep learning with 3D LiDAR data. In the context of autonomous navigation, urban object detection is crucial for ensuring both safety and accuracy. Among various urban features, poles may seem trivial, but they play a vital role in localization, mapping, and infrastructural awareness. However, detecting poles presents challenges. First of all, their small physical size, it makes it very hard for them to be spotted. And second, frequent occlusions by cars, trees, and pedestrians. And finally, the sparse nature of LiDAR point clouds, which often fails to capture the fine vertical structures, especially in higher altitudes. This thesis addresses how we can overcome these limitations through sensor fusion. Therefore, we ask these following research questions. How can we accurately detect urban objects like poles using a combination of 2D and 3D data? What improvements can sensor fusion of LiDAR and cameras bring to detection accuracy and robustness? And lastly, how can the developed system handle challenges such as occlusions, cluttered scenes, and dynamic environments effectively? And based on these questions, this project offers three key contributions. First is the fine-tuned 2D object detection model that is specifically for pole detection. Second, a 3D localization pipeline that projects the 2D detections to the LiDAR point cloud. And third, the resulting systems offering a lightweight alternative to full 3D detectors by using fast and robust 2D detections, and through this improving both efficiency and creating a real-time feasibility. Here is the problem statement. To elaborate, poles are critical for urban mapping and autonomous driving. But detecting them is inherently very hard. They are often occluded, very thin, and may appear in unexpected positions. LiDAR alone rarely gives us a full 3D representation of a pole. And moreover, pure 3D detectors struggle with these vertical, low-volume structures. So instead of relying solely on LiDAR or retraining large-scale 3D networks, my approach fuses camera-based detections with point cloud data, providing a more agile and adaptable solution. Here is the method overview. We start with a training data set and we pre-process it because the first data set was not available in bounding boxes, and it was only available in segmentation. And later we used a pre-trained model to fine-tune it with our own data set and make it full specific. And later on, we use a custom data set with images and point clouds to detect the poles in this custom data set with the model that we trained from fine-tuning processes. And then we use these 2D bounding boxes to project them onto point clouds. And we cluster these point clouds. And later we use outlier rejection, ransack to be specific, to find the 3D bounding boxes. Before this, I would also like to talk about SAI method, which is presented by Aktaş. SAI stands for Slicing Aided Hyperinference, and it is a method that improves small object detection by slicing the image into smaller patches before running inference. And this allows the detector to focus on local details, and therefore it increases the chance of identifying small, thin objects like poles. And this was added to this project to increase the 2D detector performance. You can see the results of the 2D detection. This is the images are from A2D2 datasets. And the impact of SAI is especially significant in recall. As you may see, there is a 70% increase in recall. And the precision also increases by 21%. However, the intersection over union does not face such a big difference. Actually, it decreases a little, and the inference time is severely affected by using SAI. I would also like to talk about the custom dataset that we use for the 3D parts. It is captured by Autonomous Mobility and Perception Lab, which the project was conducted in as well at UC3M in Madrid. The sequence that we used for this part is recorded in Leganés, which is a suburban part of Madrid, and it uses synchronized LiDAR and camera sensors. And this was, as said, used for the 3D localization stage of the project to project the 2D detections onto the LiDAR data. You can see the results of the 3D localization. The first image shows the full point cloud before any projection. The second image shows the point cloud after the projection. This is the conical shape that we see when we apply the 2D detection parts. So we are only focusing on what is inside that 2D detection. And the last image shows us after we cluster it and we use outlier detection to find the pole itself. This is the LiDAR points that fall on the pole. Unfortunately, this dataset is not annotated, so I had to conduct a manual inspection. And through this manual inspection, we found 580 true positive, 11 false positives, and 169 false negatives over 150 frames. And the results are quite good. The precision is very high, 0.98, so 98%. The recall is 77%, and the F1 score is 86%. So we can say that when there is indeed a detection, there is most of the time a pole, but the model sometimes fails to find the smaller poles. You can see the video of this. This is the sequence that was recorded in Leganes, as I tell you. That this is the streets that I conducted my internship myself. You can see the creation of 3D bounding boxes and the 2D detection boxes. And you can easily see that indeed when there is a 2D detection, there is also a correct 3D bounding boxes as well. To talk about the limitations and future work, naturally the system has some limitations. First of all, the training data is quite limited in diversity, and the model may not generalize perfectly for the for every environment. And second, there is a real trade-off between real-time and SAI improvement. We lose on the real-time feasibility when we add SAI, but when we add SAI, we get much better recall and also precision, actually. And third of all, geometry assumptions. The 3D localization part relies on geometrical assumptions that may not always hold true. For example, it assumes that the width and the depth of a pole is equal. Also, a pole should start from ground zero and it should be vertical. So, for example, in a case that a pole is fallen over the road, it will not take it as a pole. So, and for future work, if I had more time, I would have probably work on the annotations, because it is not very easy to conclude the project without having the quantitative analysis. And yes, I think more or less this is what I would do. What is this? I don't know how to take it off. Sorry. Thank you so much. I can take any questions if there is any.
Thank you very much. And Emma has a question immediately.
Yes, so when you're talking about poles, what do you include in the definition of poles? I saw that streetlight poles and road sign poles were included, but is billboard legs or fences, or what kind of poles are you working
Fences
with?
Are not, because I pre-processed the 2D data set as well, I didn't include fences as poles. So for example, the traffic lights, the pole part of the traffic lights, traffic signs, maybe some posts, the pole part of the posts, these kind of infrastructure are considered as poles in the scope of the project.
And in case of street lights, is it only the straight part, or did you include the upper?
No, it is not. The light part is not included.
Okay.
This is more of detail work. There's indeed a lot of work on traffic light detection. So I wanted to focus on something else that is not very well discovered and explored.
Okay. Thank you for the great presentation as well. It was really nice.
I also have a similar question. Is do you want to extend the types of objects that you want to discover this way? And if yes, this would mean that for all kinds of objects that you handle this way, you would need to run the same algorithm parallel, or can you generalize it to handle more type of objects?
It can actually be generalized very well. The same project cannot be used, but only maybe working on some smaller parts. Like the 2D model is specified for pole detection. I find it for specifically poles. So therefore, it will only detect poles. But if the 2D dataset that was worked for fine-tuning the pre-trained model is annotated for some other object, the rest of the work will comply with this. So the only thing that needs to be replaced is the 2D detector, but there is not much pole detectors, and the existing models don't detect poles, but most of the time the already existing models are able to detect a lot of different objects as well. So I don't think it would have been major work to do this for applying to different objects.
Great, thank you.
Also, especially because we are working with poles, the amount of LiDAR points that fall on the poles is 4, 5. You could have seen it, and like you have seen it in the 3D detection slide, that it is, especially for pole specific, very hard to detect a pole by only using LiDAR points, and that's why I wanted to focus on specifically this as well.
Yeah, I see why it is a tough job.
Thank you.
Does anyone have a question to Selin or any of the other previous presenters? I don't see questions, so thank you for all of you for your presentation and giving time for everyone and sharing your work. Also, thank you for Donny. I think he's not here anymore, but it's okay. Thank you. We will close this session now.
Thank you. Bye-bye.
Bye-bye.
Thank you, everybody.
Bye-bye.